case, for example, you write this, that would be an incomplete solution, or it means you didn't understood completely, the definition. But in this case, it would be this, okay? That's first step. What else? I think here we're using some variables defined as R0. It's like the root square of x squared plus, x0 squared plus y0 squared, and theta 0 equal tangent inverse y0. Given that x0 and y0 some specific values, r0 or theta 0 are also some specific values. So in this case, when you notice that if we have this expression, it's equivalent to say that x0 and y0, and we write this in terms of r0 and theta 0. This is very similar to say, for example, if this value was x0, y0, how much is this? R, right? R0, right? Is the magnitude of that vector. And this would be theta 0, right? That is the angle that such that the tangent is y0 divided by x0. Okay, so writing this form is equivalent to write x0 as what? It's equivalent to write it as r0 multiplied by cosine, right? Cosine of theta 0. And y0, right? R0 as, or multiplied by sine of theta 0. Okay, so let's replace that here. So instead of x0, we will write that r0 cosine theta 0 cosine theta plus y0 Here I will factorize r0 and these two terms, and what I get left is cosine theta 0 multiplied by cosine theta plus sine theta 0 multiplied by sine theta. Do you know an expression that can simplify that? Cosine theta 0 cosine theta plus sine theta 0 sine theta is not other than the cosine of the difference, right? Cosine of theta 0 minus theta. Minus. Okay. So we can, yeah, something similar. But this, there is a difference, right? Can you notice the difference between the one that I write here and the one that is in the slide? Negative, right? Negative. But that's also another useful property of delta function. Is that the delta of x is the same as minus delta of minus x. Okay, so it's possible. No, because the symmetry, and when this is 0, also this is 0. So yeah, they are symmetry properties. So write this is equivalent of writing delta of the negative to this. So t minus r0 cosine theta 0 minus theta. Okay? Is there a difference here with that now? Oh, it's okay, it's the same. There is one small difference here. I wrote cosine theta 0 minus theta, so that there is cosine theta minus theta 0. But you know, right? So cosine of minus theta is the same as cosine theta, right? You should first Radon transform of a delta function. So the Radon transform of a delta function will be something that looks like a delta function. So something that in the domain P theta, in this domain, when this is going to be, or when the delta function will be 1, no? Will be something. And when the delta function will be 0. When we need to look in the delta function, the argument of the delta function. So this is very important. We need to look when this is going to be 0. Whenever that happens, it means that there we have some value, some information.
Y si nosotros hubiéramos usado una versión alternativa normal de un integral, hubiéramos obtenido el mismo valor.
Se supone que sí, se supone. No sé si es tan fácil o no, pero ¿qué tal intentamos? Intentemos, ya que estamos en esto. Tan simple. A veces es un poco difícil dar la forma, ¿no? Y en este caso, bueno, coincidió fácilmente. Pero probemos, ¿no? A ver. Y hemos hecho algo así, ¿no? Una integral de delta x menos x0, algo así. Ah, ya, pero la definición era, no era f, era f,
P coseno.
ajá, era así, ¿no? Integral, ya. Entonces, en este caso, ¿cómo sería exactamente, no? Sería este es como, entre comillas, ¿no? El x, este es como que el y. Entonces sería, nuestra función es delta de x menos x0 y menos x0. Entonces sería reemplazar aquí, ¿no? En lugar de x, poner todo esto. Y en lugar de y, poner esto. Y entonces, en esta parte, claro, es no, hay que hay algo. Estoy equivocando con la definición. Fxy. Está bien así. Parece que se complica, ¿no? Es difícil despejar. Y como que perdemos un poco el tema de la doble integral, ¿no? De la definición delta Dirac.
Me preguntaba porque como el P coseno ya no tiene el T al integrar eso, no se perdería
Se supone que después de esto no debe quedar ningún t. Okay. Ese es lo principal. esto sería como de reemplazar, ¿no? Todo esto que sea cero, ¿no? Y para qué valor de t da eso, ¿no? Igual aquí, ¿no? Reemplazar esto a cero, ¿no? Y ver qué valor de t da. Creo que es lo que intentaría primero.
Pero igual no saldría como esos términos en referencia a lo que estuvimos
¿Cómo?
saldría como dos funciones en base a PS a X sub 0 y X sub 0. Y luego, como para que no salga como este término que nos salía.
Bueno, nos tiene que salir lo que trae. Nos tiene que salir a ver que era de x sub 0. Algo así nos tiene que salir. Ajá. Sí, mira, no lo sé. Creo que voy a intentar este y ya no lo veo para el otro lado. En este caso no funciona mucho, ¿no? Para esta función delta. De repente para otra sí funciona. O sea, no es más fácil de interpretar. Está bien tenerlo a la mano. En todo caso, de aquí es importante, esta parte, ¿no? Ver cuándo esto va a ser cero. And that term will be zero when e minus r0 cosine theta minus theta 0 equals 0. So in other words, when t equal r0 cosine theta minus theta 0. Okay. And notice that no, we start saying, okay, what is no, the Radon transform of the delta function in some specific point x0, y0. So what is the Radon transform of this function? Okay, given x0, y0 are known, r0 and 0 is also known. Problem. And these are its values, and then we have this relation between t and theta. Right? P equal some constant multiplied by cosine, theta minus some shift. So how this function would look in the domain, no? In the domain P theta, in this plane, this two-dimension domain. This is a cosine function, right? So it should look like cosine function. And that's exactly that, right? If we look at the delta function in the Radon transform domain, we have this good. Okay? And notice too, also that it's important, other thing is that the magnitude, the values, are not the same in all the positions, right? Or should be? Should be the same or not? Well, it's delta, right? So maybe it should be the same. No, it is the same. It's the same. Because it will add, no? If we change the direction, maybe the position will change, but the magnitude should be the same. I think. We are doing a projection. Yeah, I think about it. Should be the same. Okay, so we have this theta minus theta 0. This angle basically, or it's typically plot between 0 degree until 180 degree, because this symmetry after 180 degree to 360 should be something similar. Okay, so cosine. Okay, the curve is a general sinusoid function. For that reason, the graphic representation of Radon transform is known as sinogram. To be specific, this would be the sinogram of the delta function. If we had a delta function of another point, x1, y1, probably will be a function with r1 cosine theta minus theta 1. Some other magnitude here, some other angle here. I don't know, just to put something maybe we look later. So it could be really other form of the sinogram, but it will be a sinusoid. Another example, the Radon transform of a circle. In this case, the circle is like this value is 1 and outside is 0. So how the Radon transform will look? And then another transform of the circle will look like that. Okay, let's think about that, this function, if it makes sense or not. If we have this circle, and imagine that we have our sources here, source, and detectors over here. And assuming that it's uniform, all the values are, for example, fxy equal 1 in this circular domain. How the function of the projection, the Radon transform that is the projection, would look. In this case, well, in this case, you can think that the projection in this surface, and if the value is 1, the projection will be the one that we talked yesterday, right? Basically lengths across this. So for example, for the center, that is, assuming that is p equals 0, how much would be the value of the Rodon transform. G P theta. For this angle theta equals 0 degree. Basically the length, right? If the radius is, let's say R, radius R, this should be how much? 2R. When P is equal to the radius R, and we are basically using the edge of the circle, how much should be the Rodon transform in P theta? Exactly 0, right? 0. And in a more general position, let's say about this, for example. In this position P, how much is this length? One more time, no? For geometry, we need to remember geometry. It's going to be 2 times this distance, right? 2 times this distance. And how much is this distance? This is P, and this is R, right? So this distance would be the root square of root R squared minus P squared. So it should be, in this case, the value G P theta there, 2 times the root square of R squared minus P squared. So in fact, something that looks like, if we look at the function, this function is this for 0 degree. It will be like a root square of something minus P squared. Well, will be some value between 0 and the maximum, right? So maybe something like this. In fact, we have some decay. I'm not sure if this will be like a circle. I think no. Not sure if this will be like an ellipse, or maybe yes. Maybe given this form, this will look like a circle too. But definitely will be some monotonic increment, right? Or monotonic decrement, monotonic increasing from a maximum to 0. And because we have symmetry in the circle, we have the same in this side. So for 0 degree, for angle theta, let's say, this 0 degree, so around this function that I try to plot here, that goes from 0 maximum and then goes to 0 again, is given by the function in this line. It's 0, and then it starts increasing, and it reaches a maximum value in P equals 0, and then it takes value and it increases 0 again. So this curve is basically the intensities of the amplitudes here in this line. And the thing of the circle, or the interesting thing of the circle, is that if you change the source detector to another position, the projection will look the same, right? Because it has symmetry in the circle. It means that this kind of function will be the same for other angles. And that will be the case for all the possible angles. That's why it looks like constant, like independent of the angle. So that would be more or less the form in the case of zero. In this case, the Rodon transform can be calculated by using geometry and the circular symmetry of the problem. basically, yeah, similar to the one I tried to draw, right? In the square, in the case of the square, if I ask how is the Reynolds form, probably one more time the more simple form will be trying to sum the distances across the angles, the angles. And we try for different angles, you will see that the function looks like this. In this case, the projection depends on the angle, right? It's not the same at 0 degree that at 45 degree. And can you notice why? For example, at 0 degrees, the projection in this direction. This should be similar to the projection at 90 degree, which is true, right? It's 0 degree, it looks very similar to a 90 degree. But at 45 degree, when the projection more or less looks like this, in this direction, the projection will be not constant, right? It will be something here, and some maximum value around this position. So it depends on this total length. In fact, the projection in this 45 degrees in the center should be larger than the projection for 0 degrees. Right? That's why this intensity here is in fact larger than the rest. Any question? Obviously you can do that and calculate the exact function. But probably it need to be done case by case, right? Maybe when it's between 0 and 45 degree, and when it's larger than 45 degree, depending on the case. Doing the geometry part of the projection will be more easy or more difficult. In this case, the solution is more or less like this, right? When you have an angle less than 45 degrees, the projection is basically all these lengths. Total length, okay, the length, for example, the geometry you can calculate it. Yeah, some. Some last thing, all right, you can see that will be all these. Actually, a little bit complicated, but it's not that complicated. It's basically, at least for the simple case, for this simple case, in case of an angle theta, if this angle is theta, and this length, this length is A, how much would be all these lengths? Will be, the term will be A divided by cosine theta, and all this would be 2A divided by cosine theta. That's more or less the expression. More difficult case will be when, for example, here we have that all these values are 1. But what happens if, for example, I say that, okay, but in this log, the value will be 2, and outside will be 1. How can we do the Laplace transform there? No, the projection, in this case, we not be only the length, right? It will be like the length in this part, but multiplied by 2. Plus the length in this part multiplied by 1. It's like one extra weight given by the amplitude. You need to take in account when you do this kind of projection style calculation. For a more complicated image, no, that, okay, imagine that this image when there are variations in amplitude, that is more realistic in amplitudes. But again, if some image that using 0-degree projection, we have some profile, and that profile can be plotted for 0-degree. And see the values across here. And we have some curve. And if we repeat that for all the angles, we will obtain, look at this form of the Radon transform. Of a more realistic or more complicated image and a more complicated structure. The Radon transform is really something that looks like fire. Right? It's very difficult to interpret the Radon transform. That's what I mentioned yesterday. Along the Radon transform is very difficult to interpret. But the thing is that you can go back from here to here using something. Using what? The inverse, no? The inverse Radon transform or some inverse function. Okay, I think. Okay, vamos a hacer el quiz ahora en un par de minutos. Vayan sacando una hoja. Energético rayo, ¿no? Uno que tenga 35 electronvolts. Entonces será por acá. Y tendrá una alteración de aproximadamente, ¿no? 0.3 centímetros, aprox, ¿no? 0.1, 0.2, 0.3. Entonces, la atenuación, bueno, la atenuación de intensidad es E a la menos, ¿no? Por L. Entonces, sería E a la menos 0.3 por 10. E a la menos 3. Y eso aproximadamente es ¿cuánto? 0.05 y algo, ¿aprox? 0.05.
Hay una clase fue solo de porcentaje que caía en 80%, o sea, 0.11 de inicio. ¿También vale?
Ah, ya, 0.11.
Ah, 0.11 de inicio. Es que dice que cae 80%. La intensidad se reduce y pasa a 0.11 de la.
Pero no, el rayo más energía, pero el 25, propagándose 10 centímetros en un segundo, cae en una intensidad 80%. Esa es la pregunta. Entonces, de aquí vemos que sí, ¿no? Sí cae, ¿cuánto? 95% aproximadamente. Entonces, sí, pues sería falso, ¿no?
Es lo mismo. Es lo mismo, ¿no? O sea, es lo mismo, ¿no? Por el
La segunda,
no, porque la tensión
la segunda, luego lo único que cambia es que la distancia de la persona está más lejos, ¿no? Está más lejos. No, está pasa de 1 metro a 1.5 metros. Y aquí es donde tienen que usar todo lo que saben, ¿no? Todo lo que han estudiado hasta ahora. Y notar que la distancia por este factor, ¿qué pasa? ¿Decae? ¿Aumenta? ¿Disminuye? Decae, ¿no? ¿En cuánto creen que decae? Muy bien, ¿no? usar, ¿no? Cuando grabamos ultrasonido, ¿no? Veíamos que la amplitud decae en un espacio proporcional a la distancia, pero si hablamos de intensidad sería ese decaimiento al cuadrado. Entonces sí, debido a la intensidad hay un factor extra, ¿no? De 1 entre 2 al 2.25. Ahora, la intensidad está decayendo en este factor. Vamos a empezar a manipular la corriente, necesitaríamos que se incremente en cuánto. En ese factor, ¿no? A pasar de 100 miliamperios entonces a 225 miliamperios. Este incremento necesitaríamos para que la intensidad en el detector no cambie. Entonces también sería falso, ¿no? Pero por eso.
¿Ah? Ah, no, como todo se va. Pero sí, ¿no?
Ok, continuemos. X-rays, ¿no? Consider two arrays. One of the this is the same. Consider the configuration that we were talking of. Transmitters, ¿no? In a sequence of arrays and detectors also in a sequence of detectors, such that we will have like a very parallel rays reaching the detector. No, if we were talking about ultrasound, probably we talk about very narrow beams. Right? So it's similar here. The beam is narrow, but in particular we talk about this term collimated to refer that the beam in this way is very narrow. The emitted rays for a transmitter are only received by the receiver in front of it. Okay, that goes that this detector will only have information in this direction. It's not like this going in all directions, only one direction. Consider the emitted rays are monochrome and of intensity I0. No? So now we assume that the intensity in this point, no, is I0. And monochrome. What is monochrome here? Is only one energy level. Similar to the plot that we saw the quiz, no? And the plot of a spectrum, no, we saw that there can be many, no, many ranges of energy levels in the X-rays. The maximum will be the maximum or the voltage of the tube, no, or related to that voltage of the tube. But there can be many energy levels. That obviously complicates things. No, you can try to use some effective intensity or effective energy level. But in this case, let's assume very simple case that there is only one energy level, monochrome. It's equivalent to say that only one frequency. Okay. Under these assumptions, the intensity received in this receptor, in the receptor here, or in general, in all the receptors, depending on the position P, will be given by the intensity is the source intensity exponential and all this. This is the definition of the, at least without this minus that in the context of this problem, it makes sense, right? It's like how much distance the ray is crossing in the medium. And that's not only the length, right, but it will matter also the value of fxy. The value of fxy. Across this direction. So basically, how much the intensity will attenuate will depend on this length and the values across this line. And that is given by the transform, by the projection that we defined before as the Radon transform. Okay. In the last equation, the function fxy represents the attenuation coefficient of the analyzed of. A bit of algebraic manipulation allows to rewrite the equation as, and then isolating the exponential term that looks like the Radon transform will mean that we will have this log natural base of I0 divided by the intensity received. So this will be something that we can make it equal to the Radon transform. Okay. In other words, it's saying that if we are able to determine the intensity of the source, the intensity here that will be dependent on the value of P and the angle we are trying to we're using. We just calculate the log of I0 divided by I P theta, and that will be the value of the Radon transform in that value P theta. Okay, and that's it. No, and that's it's basically what we're saying with this expression is that even if we don't know the structure of this form, this object, it doesn't matter. We just need to measure the intensities that are leaving the tubes, measure the intensities that are being detected, and calculate this kind of terms, the log of the intensity. And that will give us one sample of the Radon transform. And we need to repeat this for many values of P and many values of angle theta. That way we will have a mapping, information about the full Radon transform map. And what happens when we have the Radon transform for all the values of P and all the values of theta? What we can do after that? We can apply the inverse of Radon transform to obtain fxy. So in other words, what the CT, the computed tomography, does is obtain samples in this domain, the domain of the Radon transform, this sample. And using these samples, try to derive the form of fxy, the form of this structure. Yeah, and that is, it's very obvious for some people maybe, but at least in the 70s it was not that obvious. Hounsfield was the person that tried to relate this kind of ratios of signals with log and the structure of FX1, and try to obtain some image FX1 of interest, the body or object. This is not only for body, right? It's for any tomograph, right? I think, for example, the new airport has a lot of these machines. So any airport has. Okay, what else? Hence, the logarithm of the intensity of X-rays measured in a line of detectors is related to the spatial distribution in a plane of attenuation coefficient. The computerized axial tomography consists on invert the Ragon transform measurements to make images of section planes of the attenuation coefficient of tissues. No, basically, no, the Ragon transform is this, no, and we are saying that this is the logarithm of this. And this is basically, right, when we have, for example, A minus UL, this term would be different. The attenuation coefficient multiplied by this. Okay, yeah, what else? And then a little bit of history, right? Like Cormac, no, and Country, no, to the first person that tried to put this idea, no, in actually constructing devices, no, that can measure intensities, sensor and detector. Cormac, 50, 60, 70, Hayesfield, built, no, the first machine that can measure this and try to actually make the images, no, and make some images of the tumors in the brain. It's basically locating these sources and sensors in a plane that is the plane of the intellect, right? In the case, the brain, for example, the head. A few years later, Siemens, it's a company, big company, made the first tomograph. Yeah, and they Nobel Prize for that idea, for Cormac and Conway, for that. Mathematically, it's not that difficult, right? Really. But making it work, making the machine, yeah, that probably in those years had some sort of difficulty, but they did it and they get the Nobel Prize of Medicine. Something more here is that in the past there were actually a translation of the sources and detectors. There was like one source, one detector, and this translates both at the same time to calculate lines, parallel lines. Actually, in current devices, there is not this translation process. So it's like all parallel rays are calculated simultaneously. So that makes it much faster. No, in the past, you need to translate this, and you need to rotate them to some angle, and then repeat all the procedure, all the translations, and then move to another angle, again, and repeat all the acquisitions, and all that can take more than 1 day. So, not feasible, right? Not practical. But some technology obviously try to make this is faster and faster and faster and faster. And right now, how long does it take to have a CT image? Some of you have done this procedure before? It takes minutes, right? I mean, it's relatively very fast. A few minutes only. Okay, I think we still have some of this ART algorithm to do. That is the process of reconstruction, assuming that, okay, we can measure many of these GPXs, right? Many of these values for several angles, and then how can we obtain FXY? ¿Cómo se llama? ¿Cómo se llama?
Está explicando.
Ah, ya, pero más bajito al final del clase. Yeah, you can think of the procedure of going from GP theta to FXY. Oh, it's the inverse Radon transform, of course. The inverse Radon transform. That is related to it. No, if you remember, the Radon transform are integrals. So the inverse Radon transform may have some integrals there, no, that will help to go from GP theta to FXY. Okay, that expression is not so simple, and in the past need many calculations. So what Consfield did, no, 50 years ago, was some procedure called algebraic reconstruction. So we will review some of these that computationally are relatively simple. I think it's based on matrices, constructing matrices, and trying to associate the dimension values of pixels with the measurements of this. Okay, I think we can do this next week. So I will finish today a little bit early. So, any question? ¿Alguna pregunta de algo? Hans, ¿ya tuviste la reunión con...? Ahí aprovecha para ver. Porque te comentabas que el tema del inglés a veces no dificulta, ¿no? Y de repente, no sé, si para el siguiente ciclo, para ya las generaciones futuras, ¿no? Se cambia eso.